Everyone, welcome to the second session of the ECCV 2020 Workshop on Imbalance Problems in Computer Vision. In this session, we are going to have a panel discussion between our invited speakers. And my name is Sinan Kalkan, and I will try to moderate the discussion. Right. I would like to thank the other members of the organization committee. And as the organization committee, we would like to thank the panel members for contributing to the workshop with their invited talks and with this panel discussion. We strongly believe that such panel discussions are really good points where we can discuss the challenges and talk about new research directions. This is really valuable. So on behalf of the organization committee and on behalf of the audience, I would like to thank you for your efforts. So our panel members are Bernt Schiele from Max Planck Institute for Informatics and Saarland University. And we have Boqing Gong from Google. We have Ming-Hsuan from University of California, Merced and Google. We have Vittorio Ferrari from Google and University of Edinburgh, and we have Tengyu from Stanford University. The panel members will have a chance to introduce themselves before we start asking questions. But before doing that, I'd like to set the floor for discussion by going over the highlights of each talk provided by the panel members. I will follow this order. So let me start with Bernt Schiele. Bernt talked about some imbalance problems in computer vision. He talked about class imbalance problem, the classical imbalance problem that we frequently encounter when we tackle recognition problems. So here, Bernt suggested that the underrepresented classes, tackling the recognition performance for the underrepresented classes can be considered as a few-shot learning problem and zero-shot learning problem. And the approaches proposed for solving these learning problems can be used for addressing imbalance. For semantic segmentation problem, he addressed this by learning an embedding space for both the majority classes and minority classes. And this way, he showed that we can obtain better results for low sample classes. Then in the last part of his talk, he talked about an interesting problem. So if you remove objects from an environment, then somehow the recognition performance on the remaining objects is severely affected. So if you take semantic segmentation problem, you take the input image and a model estimates semantic segmentation nicely. If you remove cars from this environment, then somehow the remaining objects in the environment are segmented very wrongly. So there's a severe effect of the context on the recognition performance of objects. And this reminds us a study from 2018 by Beery et al., where they analyzed the performance of different learning models. So they showed that if you train a learning model on a data set where you have a dominant context, like shown here, where you have green grass for the core object, and if you try to recognize this object in an environment which is very rare in the data set, then the learning performance is affected significantly. And your model is likely to not be able to recognize these objects as core. So this points to the link between context, the influence of context and low sample context and imbalance problems. So let me continue with the talk of Boqing Gong. In his talk, he talked about long-tailed visual recognition in the wild. he started by providing a really nice motivation for why we should study, they work with data sets that have severe imbalance problems. He gave different data sets, realistic data sets that have severe imbalance problems, and he strongly suggested that instead of working with balanced data sets, we should work with these imbalanced data sets to advance the field. He also provided this figure where long tail distribution can be tackled or considered as a few-shot learning problem for this part of the distribution. And this part of the distribution, he suggested he called it as a imbalance classification problem. He suggested that this has been studied a lot in machine learning, and this can be considered as an old AI problem. And addressing this part of the distribution as a few-shot learning problem under different domains like meta learning, transfer learning, few-shot or zero-shot learning is the new AI problem, he calls. Then later on, he suggests addressing imbalance problem as a domain adaptation problem. So he suggests that we can, for a data set, we can have two subdomains. We can have the imbalanced long tail distribution as one domain and the balanced distribution as the other domain. And we have two different domains for this problem, and we can basically solve the adaptation problem between these two domains to tackle the imbalance problem. I'm not going to go into the details of how they did that. They suggested that we need a factor to correct the estimated distribution or the error. And this weight can be learned not directly in one training effort, but using a meta-learning framework. So this is an interesting approach. Then Ming-Hsuan Yang talked about different imbalance problems. So he started first with a domain adaptation problem for semantic segmentation, and he mentioned that there is a severe imbalance problem here in this problem, especially in the target domain, you have less samples. They proposed a method for this. So instead of trying to make the feature distributions for the source domain in the target domain, they suggested that we should basically get the softmax activations as close as possible instead of the feature activations like performed in the literature frequently. And they proposed performing this at multiple feature layers. And they showed that this leads to much better results. Then he talked about recognition of samples for which we have, or of classes for which we have less samples. So here, for example, we are trying to recognize this object or this object, and the training data set has very few samples of these, so they have a severe imbalance problem here. And for this, they also proposed a meta-learning framework. So they first trained a model on the original data set, obtained some results, and they adapted this to the low sample data sets, called low sample classes, by integrating here what we can call as feature adapters, or basically standard affine transformation. And they propose learning these adapters using a meta-learning framework as well. This is the second point where we have seen the use of meta-learning for addressing imbalance problem. Then let me continue with the talk of Vittorio Ferrari. He talked about imbalance problems in three areas. One area is the classical class imbalance problem, where we have less samples for some of the classes and significantly more samples for other classes. Another type of imbalance problem he talked about is across different domains. So if you want to train a model that can generalize across very different domains, like for example, recognition problem in consumer photos, as well as recognition problems from aerial images and medical images, then we have a severe imbalance problem, both in terms of the difficulty of the task and the amount of samples that we have for these different domains. And this type of imbalance needs to be addressed. Then, as the third imbalance problem, he talked about imbalance owing to the physical space. So if you are working with 3D vision problems, empty space occupies more space than voxels belonging to objects. And if you try to, for example, perform 3D reconstruction and provide a supervision signal per voxel for your learning model, then the empty voxels are going to dominate your learning performance. And for this purpose, they propose using intersection over union instead of providing classification laws, or in addition to the classification laws that you can provide for each voxel. Then let me continue with the talk of Tengyu. He talked about adaptive regularization for imbalanced and heteroscedastic data sets. Tengyu started his talk by providing a really nice analysis on the performance of learning models on underrepresented classes. So we see at the left-hand side that overrepresented classes have low training and testing error, but we have severe performance issues with underrepresented classes. He suggested that if you tackle imbalance problems for such imbalance problems using sampling or loss weighting methods, we are going to observe significant overfitting. So we need other more established methods for addressing this problem. Then he introduced a really interesting type of problem setting. They talked about a problem where in the domain, in the space of samples, for some parts of this space, we can have lots of data which can be clean. And for some part of the data space, we can have less samples, and those samples can be very noisy. And if you tackle this problem, such problems using standard methods or using regularizers, then you're not going to get good results, because the amount of regularization that you need to provide to your model needs to be different for this part, the left-hand side of the space and the right-hand side of the space. So for this purpose, they proposed what they call is adaptive regularization. I'm not going to go into the details again, but I would like to highlight an important point here. So they scaled the regularization term with a factor, and this factor is depends on the uncertainty of the samples. And I think this is an important link between uncertainty of samples and imbalance. And they showed that this method can improve performance significantly. Okay, so that was a summary of the talks provided by the panel members. And we just picked up the highlights that are relevant for this panel discussion. There are obviously more details that we skipped. And we strongly encourage the attendees to watch these videos and for the details that we skipped here. So let me stop sharing my screen, and then we can go over each panel member, and the panel members can introduce themselves. Right. So maybe we can start according to my screen with Boqing. You are muted.
Oh, so I'm the first one.
Yeah.
Okay. Yeah, maybe I share 2 cents about the long-tailed visual recognition again. My personal experience mostly is on the confluence of machine learning and computer vision. So my analysis in the talk that understanding long-tailed visual recognition and domain adaptation problem is mostly from the machine learning perspective. So the long-tailed, looking at the first half, indeed is an imbalanced old problem. On the tail, we have few short learning, meta learning as I call it, new AI problem. But we want the model to perform really well on all classes. So kind of like our expectation is mismatched with what we have in the training set. So that's why I feel from domain adaptation, from machine learning perspective, actually it's a domain adaptation problem. And many of existing techniques could be applied to develop new and improved approaches for the long-tailed recognition. But that has been said in the talk. So instead here, maybe I provide another sense from the computer vision perspective. I feel it's still actually a representation learning problem. Meaning that...
Boqing, sorry to interrupt. Maybe in this part, we just introduce ourselves, where we are from, what problems we are working on, then we can talk about these issues. Right. So
thanks for interrupting me. Otherwise,
sorry,
I would keep on for myself.
We are very excited that you are excited about talking. So that there's a good sign that we are going to have a nice discussion. Maybe in this part we can you can introduce yourself, then we can go continue with the other panel members. Thank you.
Yeah. I'm Boqing from Google. I work on machine learning and computer vision, mostly high-level visual recognition problems. Thank you.
Good. Nice to have you here. Then in my screen, we have Ming-Hsuan.
Oh, hi. Hi, my name is Ming-Hsuan Yang, and I work at UC and Google. So I mainly work on object detection, tracking, and segmentation. Thank you.
Good. Then we have Bernt Schiele.
Yeah, my name is Bernt Schiele, as you said, right? At Max-Planck Institute for Informatics in Germany. And we're really working on a wide range of problems, imbalance problems. I think this is one of the key issues right now we have. Right, we know that if there's lots of data to do detection, recognition, segmentation, you name it, that really works well, right? We can make that happen, but everything has a tail, right? This is the key, right? And I think this is one of the key problems we have for the next decade, maybe, right? And we'll discuss more about.
Yep, very good point. Yeah, thank you. Then we, in my screen, I have Vittorio.
Hi, can you hear me?
Yeah.
So I'm Vittorio Ferrari. I work at Google, and I used to be in University of Edinburgh before. I work mainly on two topics, trying to train computer vision model with very little human intervention, which is supervised, human in the loop, stuff like that. And also recently on 3D reconstruction, 3D deep learning. And every time people say imbalanced, I tend to think about knowledge transfer between things more than rebalancing losses. So that's more the angle I like to think of.
These perspectives are really crucial, I think, and hopefully we will talk more about these in the panel. Good, thank you. And then we have Tengyu Ma.
Hi, I'm Tengyu Ma from Stanford University. So I mostly work on machine learning, deep learning, and their theories. So I guess I'm interested in imbalance problems and heteroscedastic data sets these days, mostly because I feel like I agree with some of the panelists that this is one of the very major problem in the future, in the next decade. And also I feel like there's headroom here for us to improve using either machine learning techniques or some other techniques.
Yep. Good. Thank you again. Then now we can go over some discussion points that we have determined beforehand and shared with the panel members. We don't need to strictly stick to these discussion points. Once we start with one discussion point, I have a feeling that we will just follow that thread of discussion, and we will just spend several hours on this. If we feel that that thread converges to a point somewhere, then we can continue with the other discussion points. At this point, let me tell the attendees that they can ask questions to the panel members using the Q&A facility in Zoom. Then at certain points, we will just follow and ask these questions to the panel members. All right. Excellent. Then, so maybe we can start with one of the maybe most straightforward questions that one can ask. So from the invited talks and from the literature, we see that for the same problems, we see very different perspectives, very different approaches. We see sampling approaches, loss weighting, regression methods, layer normalization methods, zero shot or few shot approaches, domain adaptation approaches for the same problem or problems. So when we see these different approaches, then one of the first things that comes to mind is, can we somehow unify these approaches, different perspectives, or do they have something in common which we can exploit for developing better solutions? If there's a volunteer, we don't need to follow an order.
I could start if that's that's okay. Okay, so I think it's actually an interesting question, right? Ideally, we would love to have sort of a single approach for a particular problem, but honestly, I think we are not anywhere close to being mature here. Actually, let me go back a bit, right? I think even the definition of the problems, I think we are having not really tackled yet, right? So we are talking about, I mean, meta learning, right? Where a particular architecture is trained, right? Yes, we talk about domain transfer or adaptation where it's unsupervised, semi-supervised. So there's all kinds of settings, right? And to me, I think it's good in the community. We're having a lot of ways of defining the problems. And I mean, what we do present today, right, is yet another angle to this. And I think it's great to have new angles and people should start and working on this. I'm not concerned about having sort of different approaches working on this. This is sort of the mindset of people. I think that there are different problems we have, right? There's the architectural problem that it's not robust enough. It's not general enough, right? There is this, I really want to infuse the knowledge, as Vito said earlier. I think we are still essentially not mature enough. And honestly, it's even hard to say what are the handful of imbalance problems we should work on, right? I think the ones we're talking about now, in actually 2 years only, right? They will be they're looking very different. So I think it's a moving target, right? And you know, it's interesting that we have quite a few Google people here on the panel, right? It's obviously a very, very important problem, right? On the practical side as well. So honestly, I think sort of the key is in a way more defining what are sort of, you know, nugget problems that actually are general enough, right? That we should train on and work on, rather than sort of saying we need sort of a particular approach for this. I'd rather think we should actually ideally have sort of maybe a handful, maybe 10 types of problems that are really sort of, if we can drive them home, we really make an advance. So this seems to be slightly more what I'm sort of thinking of, where we should invest in the next few years maybe, right? To understand what the real problems are. Can we phrase them as, I mean, we have this supervised, we have unsupervised. These are really clear. Even already in the semi-supervised setting, it's much less clear what exactly is the amount of supervision, what is the type of supervision, right? So, and we are in that setting, right? So if we had sort of pretty clear, I don't know, a dozen or something, a half dozen, whatever the number is, of clear settings that are really, really relevant, right? And work on them as a community for a number of years, I think this would be a real advance for the community. I'm not so concerned that we're all working on the same type of approach.
Good. Anyone else who would like to comment on this?
Yeah, I can say something. So the only underlying thing that I can find is that we want to adapt whatever we learned before to new data. And so from that perspective, you can adapt feature, you can adapt metric, you can adapt some output space, and so on and so forth, right? And so in the past, we could not even deal with the 80% of data, the majority of data. So we never worry too much about how to adapt to rare cases, right? Now that we are able to deal with most cases, so now we pay more attention to the last few, the long tail data, right? And in fact, that's one of the issues that I talked to some people in autonomous driving community. I mean, they've been saying that for most cases, they are able to do that. I mean, for pedestrians, for science, yeah, they are fine. But there are just quite a few rare cases that they cannot deal with. But, you know, that's very costly and they cannot make a mistake. So, you know, that's where they want to focus on, and it would take them a few years. I mean, I don't know how long to fix that problem. And yeah, so that I think that's a very important issue.
Is there a particular order, or can I jump in?
Yeah.
Feel free to shut, sorry.
So actually, generally, my general position is aligned with Bernt in that, you know, there are too many settings to hope that there will be the one unified solution that's going to work well all the time. But actually, what I wanted to contribute is another thought. Is in the list of methods you listed in the moderation, I would really divide them into groups. Resampling, loss weighting, things like this. They use the information that's in the training set, and they make it easier for the deep net to use this information to train something balanced that works well. It's a more of a numerical trick. It's very valuable. Now, the other things, zero-shot knowledge transfer, those are, for me, a bit more interesting. They add information that wasn't in the training set, that is somewhere else, coming from other categories. Typically, in my own work, I like to come from other domains. But point is, if you have just a few horse samples, like classic, okay, you could rebalance them, but maybe you can go and hunt for more somewhere else, or maybe they're not exactly horses, but they bring knowledge that help you classify them. And this in the end is what motivates me the most, is how do we reuse knowledge, reorganize knowledge in a way that we solve computer vision in general and also address imbalance problems, but more than from the perspective of rebalancing, we address it by making knowledge-wise them more balanced, because elements of knowledge come from other data sets and other tasks. And because this is such a different nature of how the problem is solved, I would separate the two buckets, the moderator you made at the beginning. Maybe we can have a unified solution for each of the two, maybe, but they're really two different nature to unify within.
May I add some thoughts?
Yeah, sure.
Yeah, so I guess I think I agree with most of the people before. So like I personally feel like we probably want to diversify the tools instead of like unify the tools. For me as a machine learner, for me I think part of me tells want to have a unified test bed. But of course, I know that it's not always the case that you have a unique setting and unique test bed. But I think for some part of the problems like class imbalance, probably we want to have a little more unified benchmark data sets so that we can compare with each other and focus on a particular setting. But of course, as I said again, there could be other more and more settings. So I feel like it'll be useful if there are some kind of like a commonly agreed benchmark data sets for different settings, and then we can try to actually diversify our tools just to see whether some other tools can also work as well.
Okay, maybe I can also add one sentence.
Yeah,
I want to echo Bernt's point at the beginning that we should actually diversify the portfolio right now, because this is the beginning of this problem, I feel. And meanwhile, I want to extend that point to the dataset a little bit. So we want to have ideally not only one or two datasets, we want to have 3 or 5 different datasets for different problems, like a classification, that's certainly one of them. Object detection, segmentation. Vito also mentioned a few tasks in the maybe a little low-level computer vision problems. The idea is not only to provide the test bed for practitioners, but also actually try to attract interest for people who work in different fields. Maybe they worked on detection. Once they saw the new benchmark, they can also jump into this boat and to continue to invent new approaches for this long-tailed recognition problem. Tengyu mentioned that maybe from machine learning perspective, we feel our paper, the long-tailed ImageNet, could be one of the benchmarks for classification, but definitely we still need new data sets for classification, segmentation, and low-level computer vision problems.
Okay, thank you. Maybe I can add a counter argument so that we continue with the discussion. So, for example, when you analyze the different strategies for class imbalance problem, we see that they particularly target the decision boundary between the dominant class and the underrepresented classes. And when you close analyze from that perspective, we see that the decision boundary is biased towards the dominant class, and we see that the boundary is shifted towards the negative in a negative manner for the underrepresented class. So by looking at the different approaches, we can maybe find the common factors that these different approaches tackle or rely on, and we can basically develop our solutions, maybe better solutions. We don't need to unify all of them. We can develop better solutions by exploiting these common factors. Would that be possible? So if these different approaches solve the same problem, there should be something common among them. I think exploiting them can lead to better solutions. Well, would you agree with that?
I personally agree. And in a concrete example, maybe the recent contrastive learning based self-supervised learning, they try to have kind of a uniform placement of all the data points in a hypersphere. Mm-hmm. And that essentially tried to place the points far away from each other. But ideally, all the points belonging to the same class should be clustered in a condensed region on the hypersphere. If we could do that, I mean, ideally, this long-tailed recognition problem won't be an issue anymore. That's also, there are some positive results for domain adaptation. So if we do that, it indeed works really well for domain adaptation. That's one thing proved in the existing work. But what remains unknown is whether that's gonna work for the long-tailed recognition. But in that sense, I agree with you. So, and a concrete example is the contrastive learning might be indeed a common factor to collect different approaches.
Okay. Any other comments regarding this?
Maybe to the first part, I wasn't entirely sure what you were talking about in the second part, but the first part you really clearly argued, right, that the the classes that are less represented, right, imbalance, right, lower frequency, they have really sort of not the same score at the end, or so same weight at the end in the output of our methods. And that's absolutely true, right? And I think that there's two things here to say about this, right? The one is actually I mean, it used to be that we're not looking particularly in zero-shot and few-shot learning. We didn't look at the generalized setting, right? Where basically you have to look at the few-shot classes as well as the the base classes simultaneously, right, while evaluating. This is really was an error, and I think it has been rectified by most papers. We really should insist that people also show this generalized performance. That's the one point I want to make. The other point I want to make is actually that our current methods are basically not particularly good, and I think that's something you want to get to later too, about given the uncertainty, right, about their estimate, right? We are giving just a score or some label, whatnot, but the uncertainties we're giving are totally overconfident, right? Both for the base classes as well as for the less represented classes. And I think this is really troublesome, right? So because we really don't have this reliability in the scores right now, it's only tuned in a way to the classification, and classification is not as 0-1 as we tend to do it and use it, right? So there's something in psychology, right? So everything, whenever you see a particular object, let's take a car, right? A particular car has a typicality for a particular car, right? If you see a very strange colored car, you still would say it's a car, but you would not say it's a very prototypical case. You would rather take sort of a particular, I don't know, whatever car looking, right? So that's a prototypical car, which is really something we really say it's sort of we have a very high certainty. So if you have not seen many cars, right, you would be much more uncertain, right? And the same is if I show you some bird classes, right, where we are probably, none of us is a birder, I don't know, but typically if you see a single sample of this, right, you will be very uncertain to recognize that particular bird later, right? So, but you know about this, right? So you're able to talk about your uncertainty about this classification. And the current models we have, people working on this, right? You also have some work in that space, but there's far too little, in my opinion. And I think this is extremely important in this context of the imbalance problems.
Yeah, I think these are really good points, and we will come to the link to how we humans solve these problems, and maybe we can continue on this point there more. Anyone else who would like to comment on this?
I mean, actually, more than commenting on what you exactly said at the beginning, I'm more like continuing on Bernt last point. I mean, the thing is, this battle between uncertainty and performance is pretty deep nets. So if we want to be able, I mean, traditionally in machine learning, if we wanted to be able to assess that a model produces a prediction and also at the same time estimates that it's not confident about it in a meaningful manner, not just treating the softmax output as a probability, then typically you need to go for generative type of models. You know, especially Gaussian process stuff like that works very nicely. But people are not so happy these days. Discriminative dominates more just because it tends to produce better top one decisions. If you just take them on confidence class or their regression value, it tends to be better. And so at the expense of not predicting proper confidence estimates. So this has actually this tension between generative probabilistic modeling, getting confidence estimates but low performance versus it. That was already in the good old days when it was bubble and arrow graphical models versus SVMs. It's and these days with the deep nets, it comes back like there is typically you want big numbers to get published, and that tends to be in a trade-off with getting confidence estimates.
Yeah, that's a really good point, and maybe I can with this point I can continue with the next discussion point, which is very related. So, I mean, currently we are using gradient descent as the dominant method for learning suitable solutions for many different recognition problems. However, these methods were developed for balanced, clean, and static data. And because in the old days, we just had access to such kind of data. Data was limited, etc., and we could only produce such kind of data. But nowadays, we have data, we have access to large amounts of data, which is imbalanced, which is noisy, and which is changing. The distribution is can be changing in the data. So given this, do you think, I mean, since these methods were developed for clean, balanced, and static data, should we go back to the approach to the roots of the problem and maybe think of a very different optimization strategy? Maybe maybe we are solving the problems in an ad hoc manner for the wrong approach. I hope that was clear.
Again, I can start. So all these optimization strategies we have are actually basically only working in IID cases, right? In ideal cases. And we know IID is first of all not what we have, and second is the other thing, because we have this domain transfer and whatnot, right? The shifts. The second is actually even currently, right? The gradient-based methods don't work best, even if in IID setting, if I really just, you know, oversampling sort of the mean of my distribution. I always go, I start rebalancing, right? In my batches, I always rebalance things like in order to get the best performance. So we actually are already having sort of this tension between, oh, in theory, there's something that actually should work optimal if I just run the data, but we don't do that anymore, right? For best performance, right? We really start oversampling towards the tails, not perfectly in the tails, which is why we're still having huge imbalance problems, but still the current optimizations, we're doing all kinds of tricks left and right. Right. And I think there's not enough theory and understanding on what exactly is the right thing here, to be honest. Right. And again, it's very much an imbalance problem to me. And yes, I agree. We should go back to our optimization and think about it, right? What better would be. But for this, we also need to understand better what sort of the difference is in our training distribution versus the test distribution, but also the difference within the training distribution of classes and, you know, less balanced classes. So honestly, I think, yes, absolutely. The gradient-based methods are just, you know, it's the layman's thingy that we all use, right? It's simple and easy, but it's clearly not optimal, right? Even for IAD.
So may I say something about this? So I guess for me, you know, I don't know like whether this is universal or not. Like what we have seen in the experiment is that the optimization, if you just care about the training accuracy, the balanced training accuracy, then you can just reweight the losses. rebalance or resampling the knowledge. I think resampling probably is more robust than reweighting, because reweighting sometimes you just weight up some classes just way too big. So if you resample, then in most of the cases you can get perfect training accuracy. However, I guess as I said in the talk, so in most of the cases the problem comes from the generalization. So I think what happens is probably that in the balance case, we are relying on the so-called implicit bias or the implicit regularization effect of the optimizers to help finding simple solutions that can generalize. However, this kind of implicit bias or implicit regularization effect is no longer working when you have a different setting. So that's how that's why I was trying to find out other regularization techniques that can help this. So in the paper, we were trying to design explicit regularizations to kind of like complement the lack of implicit regularization. But however, maybe there are many other ways to deal with it. For example, you may design a different regularizer that can get better implicit regularization. I think maybe the problem is just the stochasticity is not enough for certain classes. So when you resample, even though you have a lot of samples from the rare classes, but still you have not enough stochasticity in those dimensions with the rare classes, right? So like even though you resample, if you resample the same image a million times, it's still the same image, right? So maybe some other kind of noises should be added to those classes, or you add some explicit regularization, I guess, either way.
Thank you.
So actually,
sorry, go ahead.
Go ahead, yeah. So I don't know, maybe I'm interpreting the question too strictly, but if the question is gradient descent type of methods, do they, they are pretty good for imbalance? Somehow I would like to decouple optimization from modeling, like in good old school machine learning. You define a training set, you find your loss, and you try to minimize it. I mean, I don't think that gradient descent itself is pro or against imbalanced problems. It's a way to get to a local minima of something that you can differentiate. And many of the techniques we hear, in fact, are swappable in and out with, resampling, that's change the training set, loss regularization, change the regularization, the layer activation tricks, all that are all in the model space. And so I don't think it's strictly pro or against. So in this sense, I don't think that it's a limiting factor in this sense, or whether it is being developed specifically for clean data. It's the array of tool around gradient descent that is implicitly biased for balanced or IAD distributions in general, like Bernt like to think of, like the way we batch data, the way we sample it when we put in the batch. Lots of little tricks like, don't sample with repetition, that the theory would say, but just random permute. How do we do the epochs, the early stopping? All those things are being tuned, are meta elements that have been tuned in a situation which is not only largely balanced, but also IAD indeed. But the gradient descent operation itself, I feel it's agnostic to this, kind of virgin is faultless.
Okay, very good point. Thank you.
Yeah, I wanted to go back to Sina, your question. Unfortunately, I have to answer no to your question. My side right now is trying to really solve real problems. And I predict kind of like time will tell if my prediction is right or wrong. For at least the next 5 years, SGD is going to continue to be the dominant optimization algorithm for all mainstream computer vision problems, at least. But I can also give you a hypothesis answer. So I came to Google from UCF. I was a assistant professor there for about 3 years. So if I was still in academia, I would probably answer yes to your question. Because in academia, my mindset is more about methodology, trying to invent new algorithms, new methodologies, care less about the results. So, so given these two different situations, the answers could be different.
So it's a really good point, and that's why we have a balanced panel, both from academia and from the industry. I think.
But no, we should have an imbalanced panel. This is the wrong panel for this workshop.
Yeah, it's perfectly balanced. Yeah. So these are really good points. So if I can summarize what Vittorio has mentioned, I mean, this is the tool. and you want to keep the tool simple so that you can address completely different problems with the same tool. If you make the tool too complicated, then adapting using the tool is going to be difficult, right? Was that wrong, Vittorio?
Well, no, you said something very correct. I mean, it's not what I said, but it's something I agree with.
Okay.
What I was more saying is the tool is not connected causally with the imbalance.
Yeah.
It is, the imbalancing comes in the data distribution, and the solutions we adopted, they change the modeling, the loss, or the model more than the optimization algorithm. But what you said is also very valid.
Yeah. Okay. Good. Any other comments on this? Okay, maybe at this point we can look at the Q&A from the attendees. There's one question: while approaching class imbalancing classification, there are two approaches that you can take: data augmentation or sampling for the underrepresented classes, or modifying loss functions class weights. How do you decide which approach to use? Any volunteers?
Short answer, I use both. I use both to boost the results, not one or the other.
Okay, so let me extend the question. So, I mean, we have more than two options actually. I mean, we can take domain adaptation, few-shot learning, normalization, regularization, etc., etc. So, how? I mean, you each has your own type of approach, but for a layman person that is just starting to work with an imbalanced data set, what would you recommend? So which approach is the best in terms of, let's say, performance, or in terms of ease of adaptation, etc.? So can you comment on the approaches, the different approaches?
I could make one point in that context, which is, not really related to this, but I think that's something I think we should think about. So there is this, in the semi-supervised setting, there's this famous example where few training samples for a certain number of classes, and for others I have more supervision. My model assumptions have to be more correct than if I have actually a reasonably large amount of data. So there's this famous example where you have actually data from two classes, and if you have a linear, I forget, so there's 4 samples, right? But it happens to be that these 2 samples belong to one class, and the other belong to this class, but they have a distribution that actually covers this, but really the 2 classes are here and here. If you have 4 samples, right, and then you have a linear classifier, you basically do a perfect job in separating the classes with the absolute perfect base error. However, as soon as you use more and more of the unsupervised cases, right, you're starting to basically find the middle linear classifier, which basically screws up everything, gives sort of the worst error possible, which is 50%, right, in a 2-class problem. Anyway, so what I'm trying to get at is in an imbalance problem, we have to be more careful or better about the model we're using. And right now we're pretty agnostic. It's just running our favorite CNN architecture, whatnot, right, on the thing, and we are not considering what the proper model would be. So somehow, and that's, I mean, we are just throwing an architecture, right? And we're trying to fix symptoms of actually this being overfitting or whatnot, in my opinion, without actually being really sort of better in saying, oh, if I have a single image of a particular class, let's take, again, take my car example, and of a horse, I might actually have a different model of that feature space. Maybe the horse is more, more distributed in feature space than my car class in feature space. In that sense, I would actually need a different model or classifier for this, but we're totally ignorant to this. So this comes back a bit to what Vito said earlier. We need more about the knowledge, right? If I mean, I'm not saying necessarily it has to be high-level knowledge about sort of some Wikipedia articles about describing objects, but I'm really thinking about knowledge about sort of how the feature space is distributed, how my other samples would be distributed around my my one sample or few samples I have. All this information, all this knowledge, right, that I can gain from other classes potentially or from external source, whatnot, we're not really well using this. Plus, we're not adapting the model to these classes. So I think it's a whole complex that we're using sort of the same models with some simple augmentation techniques, a bit of sort of knowledge sort of, bit put in here and there. So it feels like the kitchen thinks and everything else. And then yes, we get a bit better numbers, but we're really not solving the problem that really few samples should give us a lot of information, right? So I honestly think we're having a trouble that we're just throwing and trying things rather than really trying to solve the problem, by better modeling.
Okay, thank you. Any other comments for this? So comparing different approaches.
I guess for a layman person, the first thing you want to try is the reweighting, right? Or resampling, right? Just because your training for the rare classes might be super bad. Only for, no, that would be the first thing I try. But of course, there are many other techniques.
Yeah, that would be the easiest things that they can try. Yeah. Good. Thank you. So maybe we can continue with other points of discussion, then continue with they take more questions from the attendees. There are some questions, but let's try to balance things. Recently there have been studies linking imbalance with uncertainties of samples, both prediction uncertainty and model uncertainty, or epistemic uncertainty and aleatoric uncertainty. This has been also used by Tengyu, for example, linking uncertainty with imbalance. So this is, I think, really an important link between two different concepts. And moreover, Bernt Schiele highlighted in his talk this case of the influence of context on recognition of other objects. So a non-common contextual situation can cause really weird errors in predictions. And recently there were some studies that continued on this using, for example, causality. So in the example of the cow, so cows usually exist in green environments, etc. And if we use our correlation-based methods, they are affected by the correlation between the grass and the object. And when you test it on a low sample context, then that correlation severely affects the recognition of the object. So the supporters of causality, Udaya Pearl and others, suggest that we should use causal reasoning in our learning models to be able to tackle such problems. They claim also that apart from tackling such imbalance problems, they argue that they can solve much higher ladders of intelligence with such causal models. So then the question is, there is a link to uncertainty, there is a link to causality. So to what extent can we utilize these information in solving imbalance problems and developing solutions? So maybe we can start with Tengyu, because you are already doing some related things with this.
I guess I don't have too much to say beyond what I said in the talk. Maybe just one sentence summarizing what we did in the talk. So we are saying that you should regularize those examples that are more uncertain or rare. So I guess if the example is very, you are very uncertain about it, or maybe the example is ambiguous, you should regularize it. Or if the example density is very low, then you should regularize it. So I think this is consistent with the kind of classical statistical learning theory on how do you regularize things, even though people are mostly thinking about one-dimensional problems in non-parametric statistics, or like just a uniformly noisy and data set. So, but I guess, I think the one, I guess maybe another thing I would just quickly say with one sentence is that estimating these kind of uncertainties is pretty difficult by itself. So we are using a very heuristic way, which is probably not right, like at the end. So it's only a very rough approximation. And the calibration of the model seems to be super important as well. So so maybe one thing we can do is to say something like there's some bootstrapping effect. You first do some better calibration using your data, and then you use the calibration to improve your data performance in some way.
Okay, thank you.
May I ask Tengyu a question?
Yeah, sure.
So what we observed in experiments is neural network is not only a classifier, basically still a very strong part is the feature extraction. So our approach is a weighting approach, but in order to get good results, we need to train the model in 2 stages. Stage 1, just using traditional cross-entropy learning, no weighting at all. Let the model see all the data, even in your term, overfitting to the head classes. It's okay, as long as it sees all the nuances and information in the dataset. And the second stage, we can use weighting to correct the mistakes. The first stage, the classifier learned. But then going back to your regularization techniques, do you feel we should apply it since the very beginning, or it makes a little bit more sense to maybe apply it later on?
Yeah, I think so in one of the earlier paper we had, so in the last year's NeurIPS, we also tried this so-called deferred reweighting technique. So you with the large learning rate, you don't reweight, and then when you decay the learning rate, you reweight. And the hypothesis we get there is almost the same as you said. So with the large learning rate, no reweighting, you get better features. And if you reweight, you overfit to the rare classes in the feature sense. So that's why your feature quality got decayed. So I think basically now, 1 year after this, what I think what's happening is basically this is why fine tuning is doing better than joint training. So I guess we know that if you want to do transfer learning, one way you can do it is you train on the source and then you fine tune. That seems to do better than joint training in most of the cases. So joint training means you just learn jointly with 2 heads, or maybe with 1 head, depending on whether you have a different task or not. And there the problem is that you overfit to the small data set in terms of the feature. So the feature is overfitting to the small data set. So, and if you do this deferred reweighting, basically you are enforcing that in the first phase, you are learning a good feature, and in the second phase, you are just doing fine tuning on a rare data set. So that's my understanding, which is probably almost the same as what you are saying. And regarding the question about whether the regularization should be applied in the beginning or not, so in a new paper we wrote this year, we didn't try to do the deferred reweighting, and we found that it's still better than what we had before. So we didn't try the deferred reweighting with this new regularization. So we started with using it at the beginning, but we do estimate the uncertainty without the regularization. So basically what we do is we first train a vanilla network without any tricks at all, to estimate how uncertain each of the example is.
I see.
As I said, maybe that's a very bad approximation, but that's a reasonable one. And then we redo it again with the regularization.
Okay, thanks.
All right. Can I follow up on the technical detail, which I find very interesting, on the transfer learning with fine-tuning versus joint training? So one important implementation detail when people do that classical thing is that the learning rates in the training on the source dataset are a lot higher than when you fine-tune them on the target second dataset. So, and that is an important technical detail. Typically, the target one is smaller, and one way people kind of avoid completely forgetting the source one and overfitting the target is that they, like the name says, fine-tuning, they actually apply much lower learning rates. And I think that it's much easier engineering-wise to train optimally for a source dataset, say ImageNet, classic, and then find the appropriate learning rates for fine-tuning on your target, Pascal or Web. So it's much easier to do that than managing to balance the training samples in a joint one block training process with all together. I think that's why it's more used. It's more of a implementation detail behind that makes it easier to deploy. So that was a technical point, but I was actually, am I allowed to completely hijack this on the beautiful Bernt Schiele cow example?
Yeah, sure.
Yeah.
I really love that that example there, and I didn't know the Terra Incognita previous paper that shows similar things. I was happy to learn about it today. I love that because it's a anti-Torralba kind of it's like building a career on Salient context helps, and now we have the examples where it doesn't. It's actually tracts. I'm not so surprised. I was also happy to see in Bernt's talk of the subtle effects of context, although the models used do not have a explicit context modeling because of the way the receptive fields of the networks operate. It goes all over the image all the time. So this brings me to my point, and maybe it's more related to the third question. The thing is, can we reduce this problem, for example, with techniques that Bernt mentioned today? But can we hope to solve it completely feed forward? When I really look at those cow examples, my mind goes between vision and reasoning. I can feel it. I can feel it in my own head. I look at it and I start thinking, oh, wait, it's a bitch. Wait, let's go back. And it goes very fast, but the boundary between vision and general AI or thinking or reasoning, symbolic reasoning, it's quite fine. In a human mind, you don't feel it. It goes all the time. And in computer vision, we're very compartmentalized. We think of it as pixels coming in, features coming out, and then all feed forward, off you go. Or we look at other communities that do reasoning and stuff like that. But in a human is mixed. And I just want maybe as a challenge, will we solve these out of context problems really satisfactorily without straddling into reasoning? Just features up. I'm not sure.
Yeah, this is a really good point. Thank you.
Yeah, I like Victoria's comment. Sorry. So yeah, so I was thinking about the same thing, context priming and all that. And even in ECCV, I think around 2008 or 2010, there was one of the best papers that used context to increase detection result. And so then back then, we're still dealing with big data. So the main goal was to increase accuracy by using whatever information you can find surrounding the object so that you can either efficiently detect object or recognize object. So yeah, and the example are very interesting. Yeah, I mean, when we drive on highway, if you see a car sign on a billboard, so if you apply standard computer vision algorithm on that, well, if you do that, if you run scanning window one by one, yes, you can detect that. But if you use some context to do that, then it will be very difficult to detect that, right? Because again, it's out of context, as Victoria just mentioned, right? So I guess we are swinging back and forth, and yeah, and the critical question to ask is how to add more high-level information or knowledge into that, not just simply just based on whatever low-level or let's just say mid-level feature we can find around object or within object.
Hi, can I just say something? Oh, go ahead.
Oh, yeah. You are here. Okay. Another thing I would add is to use some sort of active learning to find some more information if we are not certain about data. Yeah. No, take over.
Yeah, sorry, I was tied up here. This got a little late. I mean, that's a great discussion. I mean, we went through a phase like 10 years ago where it was all about context and lots of graphical models and trying to reason about context and so forth. But it's a really, really hard thing because context helps, but it can also hurt, as we're seeing here. And there are cases where you totally violate context, like cars don't fly, but I can go to a Terminator movie and can see a car coming out of a building flying, and it doesn't really affect at all my ability to the fact that violate all the norms of context or whatever. It doesn't really make it any harder for me that it's a car. And so it is that I think what's really hard is how much do you rely on context, and sort of these networks are basically just doing it blindly, and so they over estimate or the importance of context to some extent. But that's probably because statistically that's the best thing to do, on average. And I think it also has to do with the way in which our metrics are. So we favor just minimization of error and so forth, and that encourages the overemphasizing context because that's the most like the safest strategy to some extent. But causality and things like that, they're really instinct. But we've also tried that, and it's really hard to get the balance right because context and invariance are problems that are very tough because you want to have them to some amount, but you don't want to sort of if you're totally invariant, then a 6 and a 9 are the same thing. So you still want to be able to distinguish them, and so the question is like, where do you put the where does it end, or where does it start? And it's a really, really difficult thing to do.
Okay, thank you. I think these are really good points. The link to how we solve this problem and the difficulty of integrating causality or other bits into this problem that really complicates our solutions, even though they may be helpful. I'd like to maybe continue with Bernt, since you explicitly worked on this problem, you came across this problem. I'm curious whether that was an accident that you observed, that when you remove objects from the environment, it leads to a completely erroneous result, or did you explicitly expect that?
No, I mean, we did that by purpose, right? So no, we wanted to, I mean, it's again, the story about in the testing set, we don't have all the cases that we'll ever see, right? So in order to understand actually what the cases are that actually don't work for our approaches, right? We really wanted to manipulate the scenes, right? And we started in the nearest paper to actually, really literally, automatically take objects out from the scene, right? Just having a label here, right? So, but really trying to get scenes without a particular object and then using that as testing. The examples I showed during the talk were essentially sort of the cases that we found to literally, right? So that actually, well, they're out of context, right, for the system, right? But the point is, it's not out of context for us humans. I mean, I don't even have to go as far as that the flying car from the building, as Nuno just said, right, in Terminator. It's really sort of, I just take the car off the street, right, and then the street is not recognized anymore as street. So it's really sort of simply, we're not going to have all the data that we need ever to train things. My favorite example is sort of the little girl running in front of the car, right? All sort of the driving companies want to avoid, most likely, I would assume, right, to run over that girl. However, I mean, it's not about the labeling problem that they don't have the girl. They don't have the data for this, right? Somehow they have to understand, or you have to find the corner cases of your problem, right, to understand how far you can go. And you will never ever have the largest, the sufficient large test data for these kind of things. So it's not going to happen. So we need to have to do this in some way of generating this test case. That's where we started this process. I mean, the way I was telling it during the presentation was essentially a context problem, right? So I mean, let me 2 sentences more to the context, where I think we used to have these graphical models, as was mentioned multiple times, right, where we had a separation of concerns, right? We had the context information, that's the prior essentially, right? And we had the current image evidence, that's sort of likelihood, right? And we separated those concerns. And right now we're only getting the posterior, right? Which is sort of, the mingled up thing. Yes, it's a good guess, but it's just the posterior, right? So we should separate concerns. And I think it's not just for context, it's important also to explain things. So to me, it's the thing, right? I can use context if I know I'm saying there is, let's say, a keyboard because it looks like an office. It looks like there is sort of there's a screen and whatnot, all kinds of other things. That's because that's why I'm thinking there's a keyboard. Plus, I see a bit of evidence of some key, something from a keyboard. But then I have these 2 evidences, right, and they can tell them explicitly. So I think in terms of interpretability and understanding, it's very important to separate concerns. And I think it doesn't stop here having this 2 components, context and sort of local evidence. So I think the other, the second part, the second part of this last part of that presentation, right? So there we actually tried really to generate samples during training, right? That actually really outside the data manifold that actually is covered in the training set. And we had actually a paper, I think it was last year's CVPR, where we had actually we had a simulated data set where we had sort of we knew the full manifold, right? We had a latent space. We could generate a forward prediction, basically sort of a font data set. which means we really knew about the full latent space. And we could say that particular part of the latent space is that particular class, right? We basically have full knowledge about the class. So now, normally, if you do adversarial training, right, you basically attack in the image space, but you don't attack sort of in the class space. And the one devastating sort of observation we had, even if you have millions of training samples of this sort of really sort of simulated data, you really think of MNIST, it wasn't digit, it was the letters, but it doesn't really matter, it was a 10-class problem. Even if you basically have millions of training samples, you will still find holes in your manifold, in the latent space, which really basically screw up your classifier completely, right? And this is something quite remarkable in my opinion, because at the end, even if you have sufficient amount of training that we would all think for a relatively small class problem, our networks are simply not good enough, basically having the small input variation to basically not giving they can really give large output variations. So our models are not, and I couldn't agree more what Tengyu said, we really need to regularize our models much more. We have to better understand what they're doing. So I think we are seeing just the tip of the iceberg, as it said, right? So, and in this problem that we're running into, that the models are not basically, we're finding these test cases which are sort of, we can't explain sort of, but there are many more problems, right, that out there, which we might not encounter in many situations because, the natural environment around us is reasonably, how to say, cooperative, right, in an autonomous driving scenario, let's say, right? So it's not basically getting the most crazy appearance of a human that would be perfectly human, but it's not sort of, you will seldomly see this. But what I'm getting is that our models are not robust at all, right? And that's one of the key problems for all this problem. And that's sort of the other part of the game we wanted to get at when we generated images, right, which are really clearly, from the classes, from the segmentation, and but still basically then really sort of misclassified by the approaches that we use at the moment.
So I found it interesting that you were able to consistently remove objects. And like not introduce artifacts and stuff like that. Is this, are we at the stage now where we can do this consistently?
Well, I mean, if you look at the images, it's not necessarily, I wouldn't claim it's sort of artifact free, right? I mean, that's not true. I mean, the real test is then going to a real test set where you have sort of out of distribution settings, where you're looking at sort of context situations where in the original training you weren't good at, right? Can you deal with this better? And in a sense, actually, it's not too surprising in a way if you start thinking about it. But we could improve on this out of distribution data sets, right? But the thing is, we found out of distribution things which are really so far in the tail that it's typically a very small fraction of your data at the end of the day, right? So we have to deal with those, right? But if I look at the standard data set, which is sort of reasonably sampled, even sort of the out of distribution data sets we found are not that far in the tail in the sampling, number-wise, you're not improving that much, even though I would argue they're really improving on extremely important cases. Again, little girl in front of the car, you want to definitely detect it, I think, right? So it will come very, very rarely. It will give you, some, 10 to the minus 5 in your performance measure, right? Improvement, but that's a very essential one.
Okay, excellent. So if there are no other comments regarding this, maybe we can link to how we humans solve the problem. There were already some pointers to that. So, I mean, as you have all mentioned, we are very good at this, right? Even if you take an out of context object, we can recognize that very well. Although maybe it takes longer for us to process that information, we can solve this. So what kind of inspirations can we take from human visual system and improve our architecture so that we can solve this task better?
Well, and then since I was the one that raised this before, I mean, maybe it's also about theoretical fascination, but the very fact that the processing is constantly going up and down in the visual cortex and the brain, as opposed to mostly feed-forward in computer vision, that always fascinated me. There is some notion of feedback that comes back and alters, perhaps not a very low-level visual feature. I guess that Gabor filters are always there, but it affects the way we interpret the image. And that is them psychophysically demonstrated by what you just said, that it takes longer to solve the problem. It takes longer by looking at it. Now, it's not like taking longer has to be a requirement for an artificial system. But what I would argue, what at least charms me, is this largely, I mean, mainly unexplored part of once we go up and we are surprised, we estimate that uncertainty, but we don't know how to estimate yet, we are able to go back and reconsider the visual cues. And this is because, in my opinion, it would be fun to go beyond a composition of prior and likelihood a bit, like, a prior structure that's maybe at the top. It's not the same as having visual features extracted on a network and passing them through a CRF that does some kind of context. It's not that, right? It's about there is some surprise, a cow on the beach that we don't recognize, then we go back and reconsider the visual features completely, maybe even extract others or reinterpret what we have seen. Maybe a certain edge means something else now. It's no longer a snowboard to snow transition, but it becomes highly monster eating Sigourney Weaver, I don't know. So this feedback process are guaranteed that it's very clear the brain does them. It's not very clear what it does with them, according to my understanding of. And it's also rather clear that although every once in a while there is a paper like that already in the 90s in vision, it's not something the community is paying attention to. And I think it's fascinating. I don't go as far as saying it will be strictly necessary. I mean, I myself did research there, but I think it's a big piece we are missing. And when I see these examples with the cow on the beach, it definitely, these feedback loops come back to me.
That's a really good point.
Yeah, to follow that, I would say, yeah. So for humans, if we receive a new gadget, what do? Well, we turn it around and we try to find some visual cues, right? So in fact, we are using some sort of active learning just to reinforce our belief based on our prior knowledge and our recent observation, and to see, okay, can I recognize this object, and then can I relate this to anything that I have seen before? And so in computer vision, we can also do that a little bit. I mean, in one of the papers we did in CVPR 2014 for semantic segmentation, for that, we need to train the online classifier for the particular test image. So once we figure out that we do not have enough example for some particular classes within that image, because offline when we train our classifier or model, it is based on the general the most popular classes, right? So for the classes that appear in the test image, those may not appear frequently in the trained model. So, but we still have data set. So once we figure out those classes, we can go back to the data set and try to find some more reinforcement, try to find some more examples so we can train the classifier online and help the model better. And yeah, so then I think we can also do it. And another thing that I will add is, I mean, but it's very difficult how to encode. I mean, we'll go back to the old AI problem, how to incorporate human knowledge, which is much more difficult problem. So yeah, I would like to hear what other panelists say. Comment on this.
So I have something to say about this, and it's kind of less ambitious than I guess the what Vittorio was saying, but it's also inspired from like the way that people solve these problems. So my concern is a little bit that we're requiring these AI systems to actually do a lot more than what people do. So people use taxonomies a lot. And there's actually not huge evidence that we're, that great, few example learners. If it's really things that we don't know about. So, for example, like we have some projects where we work with biologists on classifying images of plankton, which is something that people don't see. And nobody can learn to classify plankton by just looking at 10 images or 15 images or something like that. So there are what we do a lot is we kind of define what the answer should be. So for example, when I don't know much about horses. I haven't been trained to recognize horses. So, when I see a picture of a horse, I don't say, oh, it's a Belgian horse or a Arabian horse, or I just say, well, it's a horse. And if that answer is not good enough for you, well, tough luck. This is what I can do. But, when we train these AI systems, we want them to, always give us the answer like, at the most highly precise level of detail. And it might even, be unrealistic. It might be that it's actually not even doable, because, even people don't do that. So I wonder if there should be more room to say, if taxonomy should play a bigger role in this, and if there should be a room to let the classifier decide at what level it wants to give you an answer, instead of always trying to sort of minimize the error at the very leaves of the taxonomical tree. And so, I mean, that's not how we structure these problems right now. But I think it's a direction that should be explored.
I would also like to follow up on this a little bit. So I have a even probably more naive explanation on why humans do better. I feel like humans just have seen much more unlabeled data over the years. So for example, suppose you, and they are shared patterns, so the humans already know the features. So for example, suppose you like me to do some medical diagnosis, or I think there are also other kind of like charts or figures you want to classify in chemical domain. I think humans learn much more slower than the current AI system potentially. I don't know, at least I don't have a evidence for this, but like at least I feel I learn pretty slowly. Like I have to really know what the feature is, and sometimes like I needed the person who trained me to tell me explicitly what kind of features I should look for. Otherwise, all those kind of like images looks very similar to me. So so I suspect that this might be a very naive possibility, but I suspect that humans just learn already the very good features with the unlabeled data, and then when you give a new class to the human, then they can just match the feature with the class pretty quickly. If that's the case, then we should do more unsupervised learning, I guess.
Yeah, that's a really good point. And today I saw your tweet on a new paper that you have on this, right? Can you talk a little bit about this? Because it supports this hypothesis.
Yes, yeah. Thanks for mentioning it. I guess that's not exactly for this kind of imbalance question. So we are trying to understand why self-training can help. So so the kind of the setting we are interested in is that you have pretty biased data set. In some sense, you have a spurious correlation with there's a feature with a spurious correlation with the label. And then in the target data set, where you don't have any label, the target data set doesn't have such spurious correlation. So it's a much more diverse, unbiased target data set. And we can show that under certain assumptions, that's a more or less theoretical paper. Under certain assumptions, actually, we have very strong assumptions. We can show that if you self-train on the target data, then you can remove the use of these kind of spurious features by doing the self-training. So so I guess, just to connect back to the question already before the points before, this is also one way to use the unlabeled data, but I assume there are probably other ways to use the unlabeled data as well.
I feel that this is related to human visual system because we have the feature hierarchy for many different tasks. The features are generic and for very different types of problems. And maybe I thought your approach was relevant there because we have this feature hierarchy being trained for many different settings, many different problems. Then on a new problem where there's an imbalance or where there's bias towards some classes, maybe we are less affected because of this generic feature hierarchy.
Yeah, I agree. Yeah, I think in general, I feel like I guess at a higher level for this imbalance problem, I think if we can learn better features, certainly sounds like a better idea. We can learn the better features using one way or the other, like unlabeled data, or like Boqing says that you can probably pre-train first and then fine-tune on the rare classes in some way, or do the meta learning. I guess that's probably a better idea.
Okay, thank you. Any other comments regarding this or other points that we have discussed?
Yeah, I actually, to answer, I mean, I'm going to advertise a paper that's not mine, to Nuno, about, you were saying you wish there would be more use case taxonomy, and then you mentioned one specific idea that really activated in my brain. So you were saying, oh, we always ask them to produce as specific as possible class, and it would be nice to choose automatically at which point. There's a very nice paper by Jia Deng and Feifei at CVPR 12 called Hedging Your Bets, which is exactly this idea. The classifier tries to be as specific as possible without making errors. So if he has no idea, we just answer entity. Not great. If he feels better, we say animal, in your example with the Belgian horse. If he feels better, we go horse, and at the end, he will go Belgian horse. And he will choose at which the level of detail or abstraction he gives an answer so that he doesn't make mistakes and he got as specific as possible. It's a really cool paper. Not mine again.
Yeah, so that's but the interesting point is like because we've been trying to do this, but one difficult point is that we have this culture that's so rooted now on these results and beating the performance and so forth, that if you try to do something, see, like in order to do a taxonomic classification, you need a different evaluation criteria. And then people respond like negatively to that, like, oh, you're not doing the standard thing and so forth, and that becomes a problem. You see what I mean? Because it's like these evaluation metrics are so entrenched now that it's just hard sometimes to think in to do alternative things.
No, I believe totally. I mean, this is a general problem, and maybe I don't know if it's the right workshop to embark in a very interesting discussion about social effects in computer vision, actually. But yes, I mean, if then you need to make up a metric, and then it gets a little harder to publish. It's true. Totally. I mean, people are used to just determinately just one out of X classes. And this is also because it's propagated by challenges, and
Yep.
I still remember when we came to the COCO challenge with the COCO staff dataset, trying to add background regions to the foreground objects like, grass, sky. And so we had this nice taxonomy of background types. And, the first, correctly so, I'm not criticizing, but the COCO group said, yeah, we would love to use your data. And the first thing we do, we remove the taxonomy. And any ambiguous things we had, like playing field and grass, which is not even in a taxonomy, this is set intersection. Some things are playing field and not grass and opposite. They were just eliminated. And everything was made so that it's one out of X. Sure. But I understand, I mean, it makes it complicated to do challenges, but definitely I see the spirit in the community.
Yeah. So one other related topic, which is, it seems to me that the ways that we're addressing these long tails, like by data augmentation or sampling or, even regularization, they don't really get to the meat of the issue, which is, when we do these things, we work with analogy a lot. It's like, well, I can learn about a wolf easily because I already know about dogs. And so there's this sort of transfer of information from classes that I can do well or that I've been trained well to new classes. That's not necessarily captured, I think, by any of these ways in which we are approaching the problem. And we haven't done anything about that yet, but I wonder if what do you guys think about that? Or is there any thoughts about that?
Maybe I can give it a try. That's a very good point. Suppose we want to maybe do a thought experiment. We have a lot of data, labeled or unlabeled. In addition to the long-tailed training set, we want to learn good features such that we can transfer, for example, from dog to wolf. Exactly the analogy you gave. I think the answer is probably 100% that we can observe improvement because we observe the better features and more data and relevant data as well. But what's interesting remains is how much improvement we can get and what type of additional data could be useful for us to do the transfer. The taxonomy you mentioned earlier might be a good source of seeking the relevant data and also explicitly define the transfer path, transfer regularization, or between the additional data and the long-tailed training set we have here. But again, the question remains like, okay, if we do that, probably we can still observe improvements, but like how much improvement we can get. What's just an alternative approach, which is we don't use any additional data. Instead, we maybe design a better model using the dog to wolf type of transfer to introduce stronger inductive bias into the model. So we know these two classes might have a better transferability between each other. So we design, therefore, a very strong inductive bias into the model. Maybe that's sufficient already. So these two different type of things, I think we don't know the answers yet, but that's a very good, emotive, very, very inspiring question. So given that question, how can we approach these two follow-up research questions? One is by additional data, the other is by stronger inductive bias. I think that's something we can answer in the future. We can try to.
Any other comments regarding these? There's been 90 minutes, more than 90 minutes. But maybe slowly, if there are no other comments.
So I have one provocative question.
Okay, excellent.
Which is, there's been a lot of work on, few shot learning. Okay, now we have this long-tailed recognition problem, which in my view, it's richer and allows us to do more. So is there a reason to work on few shot recognition anymore?
So
yes.
I think it is, yeah, because I mean, I agree that few shot is sort of a sub-problem of the imbalance problem. In that sense, I agree. But I still think that few shot is not really solved yet to a level that we are fully happy with it, right? So I think it's right now the imbalance data sets that we use haven't really, I don't know, they're still sort of struggling a bit how exactly it's to be evaluated, right? And there's too many things that happen together. So I think, yes, the imbalance is sort of the next level, but I still think few shot is not done completely, that we should completely abandon it. But I agree. I mean, it's probably time to think about it in the next few years, maybe.
Yeah, for some problem, for example, for online visual tracking, we have one image. We have only one shot, if you will, and you still need to do something about that, right? So yeah, so then it's still worthwhile exploring.
And I guess just to, this is something I heard from some other people. So in NLP, they can even do zero shot pretty well. Like a zero shot is not much worse than a few shots, or even a little more shots these days. I don't know. I'm not very familiar with all of those results, but I learned this from a senior faculty who is a famous person in NLP. So it seems that if this is the case, then few shots still has a pretty important role, just because why not a fewer shots, right? So if you can do as well as more shots, so I think probably this has not been seen in vision. I'm not entirely sure either, but I'm just saying that if that's a possibility, then maybe few shots still worth doing, in my opinion.
So, but my question is related to what we were talking before, which is, if I can do wolves better because I know the dogs, then the imbalance is a central part of solving the few shot learning problem. And so if that's true, then maybe it trying to solve the few shot problem in sort of isolation, it's just too hard. It's just like we're sort of asking again the systems to do too much. So that's more, that's more what I'm thinking. And it's not, it's not like that I have an agenda to kill few shot research, but I'm just wondering whether again we define these problems and we say, oh, because people do this, but it's not clear that people do this, right? Because we never really have a genuinely few shot problem to solve. We always bring in all the stuff that we know already, right? And that's the the result of a lot of training with a lot of classes with a lot of training. So that was just like what I was wondering.
Maybe we can do big shot learning.
Well, it was meant to be provocative.
I guess I kind of agree that the imbalance setting is probably a little bit easier to use in industry than few shot. Just because you always have a big data set and you have some natural imbalance and some naturally few shot classes already there. But you don't have to artificially distinguish the few shot classes from the rest of the examples. So the imbalance setting might be a little bit easier to use.
Yeah, can I second Nuno's point of view? I feel, few shot learning, of course, it's not solved, still needs a lot of efforts to do. But I hope more and more researchers will move on to the long-tailed recognition problem. It's just a bigger room to invent, to do the invention. We need additional, maybe a few more data sets at least. We also need different approaches like additional data, stronger inductive bias. Also, as Tengyu just said, it's a more realistic problem, at least for industry. So why not? I hope more and more researchers will move on to this problem.
These are really good points. I think we had really good perspective for this from different angles, and if there are no other comments or questions, then maybe slowly we can conclude. I'd like to thank all the panel members on behalf of the organization committee and the audience. This has been really fruitful. We looked at the problem from different angles and how we can relate this problem to how the humans solve this, and different approaches like few shot learning, domain adaptation, etc. I think this has been really fruitful. Of course, there were more details about these in the talks of the panel members. We encourage the attendees to watch these videos as well. And hopefully, since this is an important problem, there is an increasing attention on imbalance problems, and maybe in the future CVPR conferences, we can have a remake of this workshop and the panel discussion, and we can continue on how few shot learning is approaching or evolving, how domain adaptation is evolving, and where we are going to be on addressing imbalance problems from different perspectives. So thank you, everyone. So have a good night or day, wherever you are, in which time you are. Okay, take care. Bye-bye.
Thanks. Bye.
Thank you. Bye-bye. Thank you.
I'll see you all, guys.
Bye.